Hello, my name is Kevin Craig. Who is an engineer? Engineers are society's problem solvers. Engineers are people with integrity who solve problems to help people without regard for egos, ideology, religion, nationality, and politics, always focusing on facts and the problem. Society's problems today are complex, multidisciplinary, and ever-changing. The pandemic, and health in general, is not the only challenge the world faces. Climate, energy, poverty, water, shelter, and education are all urgent societal issues. Becoming an engineer is an unselfish calling. Yet today, 90% of the engineering done in the world is done for the richest 10% of the world. What about the other 90% in need? You do not need to look far to find people in need of engineered solutions. For example, the disabled, the elderly, and the poor, right in your own neighborhood. Innovation is a way of thinking, communicating, and doing. How does innovation happen? Innovation happens when a human problem or need is identified, when engineering and technology identify feasible solutions, when business identifies viable and sustainable solutions, and when the solution proposed is usable as complexity is managed. What is mechatronics? Mechatronics is 21st century multidisciplinary systems engineering. It is technology integration, sensors, actuators, electronics, mechanisms, machines, computer control, all to achieve optimal system functionality with a foundation in model-based design. That is, using mathematics and physics to create a working virtual prototype, a computer simulation of the system one is creating before cutting metal and soldering wires, so that when the actual real prototype is built, it works the first time. That is how astronauts went to the moon and back 50 years ago, and this is how today SpaceX flawlessly lands a rocket on a platform in the ocean. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process, from the very start of the design process, thus enabling complex decision-making. Integration is the key element in mechatronic design, as complexity has been transferred from the mechanical domain to the electronic and computer software domains. Mechatronics is an evolutionary design development that demands horizontal integration among the various engineering disciplines, as well as vertical integration between design and manufacturing. Mechatronics is the best practice for synthesis by engineers driven by the needs of industry and human beings. It is technology integration to achieve optimal system functionality. Complexity demands a new engineering mindset. In mechatronic system design, we integrate. From the very start of the design process, we combine the physical system with sensors, actuators, computer control, and human interfaces to give it some intelligence and decision-making capability. At its very heart, system complexity is synonymous with power. However, this power can be good or bad. If the complexity in any system is not tamed, the consequences can be devastating. We have witnessed some of the consequences of untamed complexity in the Chernobyl nuclear plant accident in 1986, the world financial meltdown in 2008, and the Gulf of Mexico Deepwater Horizon oil spill in 2010. All are examples of systems of unimaginable complexity, intended or not, that were left unmanaged without common sense, human-centered checks and balances, which resulted in catastrophes of immense scope. The world coronavirus pandemic we are experiencing is the present-day example of this. Today, we've come to depend on an ever-expanding array of intricate high-tech systems. These hardware and software systems are the guts of financial markets, energy exploration, space exploration, air travel, defense programs, and modern production plants, and are too complex for any single person to understand. Yet every day, individuals are asked to monitor the health of these networks, weigh the risks of a system failure, and take appropriate measures to reduce those risks. People are not great at measuring and responding to risk when placed in situations too complicated to understand. People have trouble imagining how small failings can combine to lead to catastrophic disasters. People tend to get acclimated to risk and unconsciously adjust their definition of acceptable risk as things seem to be going well. People tend to place elaborate faith in backup systems and safety devices. People compensate for lower risks in one area by taking greater risks in another. People tend to match complicated technical systems with complicated governing structures. And people in the same field begin to think alike, whether they are in oversight roles or not. The potential for high-tech catastrophe is embedded in the fabric of day-to-day life. In a complex system, learning how all the pieces, constant and variable, interact gives a depth of understanding that averts catastrophe. That is what we mean by human-centered design, understanding the interfaces among technology, people, communities, governments, and nature. This is what makes complexity manageable. All complex systems have, as a foundation, fundamental principles or core knowledge that cannot be ignored. However, there must also be a flexibility from the engineering perspective to respond to problems which inevitably arise. Clearly, the typical discipline-specific engineer is not well equipped to manage such complexity. Not even an engineer with multidisciplinary engineering breadth can do an effective job. What is needed is the T-squared engineer, an engineer with engineering depth in a particular discipline and multidisciplinary engineering breadth. But in addition to that technology depth, that person has non-technical breadth in business, human values, social science, and in managing complexity. This is the 21st century T-squared engineer. Yes, innovation is local. You don't import it, you don't export it. You create it. It is a way of thinking, communicating, and doing. The cost of technology has plummeted over the past several decades, while the complexity in our systems that we design and the information available to us has skyrocketed. Human evolution has remained essentially constant over the decades. What bridges the gap between human evolution and the complexity in our systems and the information available to us? It is human-centered design. Human-centered design requires interdisciplinary collaboration, an iterative process with frequent prototyping, and engagement with real people. Mechatronics education. Complexity demands an engineering skill set with technology depth and non-technical breadth, specifically human-centered design expertise capable of managing complexity. Why are these engineers not being created? How do we ensure that they will be? Engineering graduates need to be able to adapt and apply technology that is human-centered, desirable, feasible, viable, sustainable, usable, and manageable. Incoming students need to experience a culture change. They need to transform from the world of memorizing, test taking, and focusing on grades to the world of critical thinking, problem solving, turning easily accessible information into insight and understanding, and taking responsibility and ownership to become an engineer. If we all know what should happen in engineering education, why is it not happening? There are two main impediments to engineering education reform. First, the silo structure in a typical engineering college does not foster reform. Engineering departments typically don't collaborate or interact in a multidisciplinary way and fail to realize that doing so would enhance, not diminish, what they do. Second, there is a failure of faculty to get out of their comfort zone, become involved in real-world problem solving, and respond to the challenges of teaching multidisciplinary engineering problem solving in a discovery learning mode, as opposed to a lecture mode. Knowledge needs to be unbundled and rebundled in engineering education to give it balance between theory and practice and relevance to the solution of the multidisciplinary problems society faces. Engineering education done in this manner can mitigate catastrophe. Is there an alternative to the upper 2 years of a university engineering education? Yes, there is. It's an innovative approach. It's called a Mechatronics certificate. In half the time of the upper 2 years of a university education, and 1/4 of the cost of that education, that is 12 months online and hands-on, at a cost of $15,000, you can become a mechatronics engineer with a guaranteed mechatronics job. The prerequisite for this program is an associate degree in science or engineering. Yes, this is an innovative approach to becoming a mechatronics engineer for the 21st century. Contact me, Kevin Craig, at this website, at this cell phone, at this email address for information. Become a mechatronics engineer to solve the problems the world faces in this 21st century.